Let's begin Section 3.2 on confidence intervals for a single proportion. Read Section 3.2 as well as the Chapter 3 intro. We are skipping Section 3.1, so the Chapter 3 intro is important to start you guys thinking about what a confidence interval is and why we should make one. So why do we create confidence intervals? Why is a single sample statistic not enough? We know our statistic should be close to the parameter as long as we've used an unbiased sampling method. But how close is close? We need to estimate sampling variability to answer that question, and confidence intervals do just that. Confidence intervals give us a range of plausible values for the parameter, or gives us a range of values that we think the parameter should be in. This includes our idea of sampling variability, as well as using our individual sample statistic. We'll learn two methods for creating confidence intervals. The first is through simulation. Typically, a confidence interval will be created after a hypothesis test was conducted. In a hypothesis test, we simulate many samples and plot the statistics from those samples, assuming the null hypothesis is true. The spread of those statistics gives us an estimate of sampling variability, and so we can use that to create our confidence interval. The 2SD method is to take the observed statistic plus or minus 2 times the standard deviation of the statistic. The standard deviation of the statistic we can find from the standard deviation of the null distribution, or the spread of the statistics, assuming the null hypothesis is true. But what about the 2? Where did that come from? Remember the empirical rule? If we are looking at a bell-shaped normal distribution and we go 2 standard deviations on either side of the mean, we should include about 95% of our distribution. Therefore, this 2SD method is specific to a 95% confidence level. What if we want to do something else? Any other level of confidence? In that case, we would have to use the theory-based methods. Remember, the theory of the theory-based methods is the central limit theorem. For proportions, that says that the sample proportions will be distributed normally, centered at the true parameter value, pi, with standard deviation root pi times 1 minus pi over n. In a hypothesis test, we assumed we knew pi, or that the null hypothesis pi was equal to pi naught was true. So we just plugged in that null value for pi in our standard deviation formula, and we're able to calculate our standardized statistic. But in a confidence interval, we are trying to estimate pi, and therefore we do not know its value, nor do we assume we know its value. So what can we use instead? The only thing we have, our sample proportion, p hat. Standard error of a sample proportion is equal to the square root of p hat times 1 minus p hat over n. Notice this is the same formula for the standard deviation, only plugging in p hat for pi. Because of that, we call this standard error, or the estimated standard deviation of the sample proportions. So plugging in all the notation for a single proportion, we get a confidence interval formula of p hat plus or minus some multiplier times the square root of p hat times 1 minus p hat over n. Again, the multiplier will come from the theoretical distribution and the confidence level. For a single proportion, we use the normal distribution, and so you should write down or memorize the 3 multipliers from page 176 in your textbook. 1.645 for a 90% confidence interval, 1.96 for 95%, and 2.576 for 99%. Notice that the 95% multiplier is actually 1.96, not 2 like we used in the previous slide. 2 is just a rounded version of the correct multiplier and works well when we are using a simulated standard deviation rather than the formula for standard deviation, which we get from the central limit theorem. Also note a change in language we use versus your textbook. We call the formula for sampling variability standard error instead of standard deviation because we are using the estimate p hat instead of the true value pi. Be careful with your wording.